Hello. So in this video, I'm going to give a very brief introduction to linear functions. And the reason it's going to be brief is that I only want to introduce these as they relate to the topic of the course, as they relate to calculus. So a lot of things you might have done with linear functions, like finding the equation of a line through 2 points, we don't care about that. What we care about really is what makes linear functions linear. A function is linear if it has a constant rate of change. If we write the form of a linear function, f of x equals mx plus b, this constant rate of change is the m. So, for example, let's say there's a disease outbreak and every day an additional 10 people get sick. I'm not claiming this is a very realistic example. In fact, it isn't for most circumstances, but bear with me for the moment. So we've got a constant rate of change here. The number of sick people is increasing, and it's increasing at a rate of 10 sick people per day. And this is constant. It's doing this the first day of the epidemic. It's doing it a year into the epidemic. It's never changing. F of x equals 10x plus b. B is the y-intercept here, but going back to what I said earlier, we're really not interested in this. This is what we care about from a calculus viewpoint. So if we graph this, I mean, the exact graph will depend on B, but this is going to be a straight line. The graphs of linear functions are always straight lines. So maybe it looks something like that. And you probably know from high school or wherever the relationship between this number 10 and the graph, but maybe you don't. And if you don't, that's fine too. This constant rate of change when we're looking at a graph is also called the slope. If we pick 2 points on the graph, it doesn't matter what 2 points. The slope is going to be this vertical change, which we call the rise divided by this horizontal change, which we call the run. In this case, the slope is 10, so the rise over the run equals 10. Now, I've indicated that this example is probably unrealistic, at least for a lot of diseases. I mean, speaking of the disease, that's probably at least a little bit still in all of our minds. It's certainly unrealistic for COVID. But the point I'm trying to make here is that we can ask a question. How quickly is the disease spreading? And that question has a single concrete answer. It's increasing by 10 cases per day. Now, if this is not a realistic graph for the spread of a disease, what would or what might a realistic graph look like? A lot of graphs representing the spread of disease are going to be what we call logistic. And the word doesn't matter. At least, I mean, I'll write it down. But at least at the moment, the word doesn't matter. But a logistic graph is going to look something like that. And now, if we take this question, how quickly is the disease spreading? And we look at this graph, suddenly there's not a single clear-cut answer like this. What seems to be happening is that the disease is spreading slowly at first. If it's contagious, there aren't a lot of sick people, so there aren't a lot of people to spread the disease. Then it starts to grow quickly, and then it levels off as the outbreak ends and people stop becoming sick. So this question is still interesting. We still want to ask the question, how quickly is the disease spreading? But now there's no single number that serves as an answer to the question. And the first calculus thing we're going to look at, it's specifically called differential calculus. And it's addressing this question. It's addressing the question, how do we discuss the rates of change of non-linear functions functions whose rate of change is not constant. So this is the motivating question of differential calculus.